This is joint work with quite some people in Bonn. And so actually it's failures of the forcing theorem in class forcing. But so let me first, does my microphone work, by the way?
Can you turn up your volume?
Turn off the, I have no idea how to do that. Okay. Any better now? Yeah? Okay, I'll try to talk loudly. Okay, so let me start with set forcing. So set forcing or forcing in general is a way to obtain new models of set of C, starting from old ones. And so if we start with a countable transitive model of set of C, which will be the basic framework in this talk, we consider some partial order that is an element of this model and a generic filter, which is a subset of this partial order. And generic means that it meets all the 10 subsets of the partial order, which are elements of our model. And then we can form a generic extension M of G, and that we do by taking all the names sigma in M and considering the evaluations with the generic filter. And I guess you all know how that goes. And so if we start with a model of set of C, we know that the generic extension M of G is a model of set of C again. And so that's why I'm doing this introduction really is, and the forcing theorem holds for all set forcing. And so what does the forcing theorem say? So let me start with a definition first. We say that P forces a statement phi if and only if whenever G is a generic for the forcing P over the model M, and P is a conditional generic, then the generic extension M of G satisfies this statement phi. And so the forcing theorem consists of two parts. The first one is the definability of the forcing relation. This says if we have a formula phi in variables x1 to xn, then there is a formula psi such that for any possible sequence of names in our model M, so M is the ground model, and any condition P in the forcing, we have that P forces phi of this sequence of names if and only if M satisfies the statement psi of this sequence of names, the condition, and the forcing P to go with its extension relation. So this means whether P forces some statement phi of a sequence of names is definable over the ground model M. And the second part of the forcing theorem is the truth lemma. The truth lemma simply says that if we have a formula in variables x1 to xn and the sequence of names in the ground model, so if this formula holds for the evaluations of those names in the generic extensions, with G a generic filter over the ground model, then this is actually forced by some condition in the generic. And so the results of this talk, or rather of the work that I'm talking about, are that the forcing theorem can fail for class forcings. And in fact, even the truth lemma can fail for class forcing. So, oh, did I go back? Yes, I think so. Oh, no, I didn't. Oh, right, sorry, yes, I wanted to introduce class forcing. I thought I was on the first slide again. So let me say what class forcing is for this talk. So class forcing should mean that instead of starting with a partial order P that is an element of M, we just use a partial order P that is a definable a subset of M from the point of view of V. So from the point of view of M, it's just a class. It's class-sized. And of course, the extension relation is supposed to be a class of the ground model M as well. And so what does genericity mean in this generalized context? Genericity now means that the filter is supposed to intersect all the dense subclasses of our class forcing P. And the generic extension is still formed in the same way, so we take all the names which are elements of M, and we look at the collection of the evaluations by the generic filter, and this is our generic extension. And so one could now think about which second-order objects the generic extensions should possess. So, I mean, you could look at the plain generic extension, which is just the collection of all the evaluations of names in the ground model. But you might also want to consider additional predicates. So, for example, it's quite natural to consider a predicate for the ground model and for the generic filter, which is now a proper class over your model. And maybe you also want to consider other predicates. This is not particularly relevant for anything in my talk except for the very next thing. So I want to start with the question whether the generic extension satisfies the axioms of ZFC. And so there are different versions of what this could mean. So you could either mean that the plain generic extension satisfies the axioms of ZFC, that is, we don't consider any class predicates, or you could say that satisfying the axioms of ZFC is supposed to mean satisfying the axioms of replacement and separation together with those predicates you might have added, like the predicate for the generic filter. And so it's quite easy to destroy replacement in a generic extension. So look at the forcing collapse omega ord. The conditions are just functions from a natural number to the ordinals, and the order is the natural one, which means reverse inclusion. And so a generic filter for this forcing gives you a sequence of length omega, which is cofinal in the ordinals by a very easy density argument. And so if we allow reference to the predicate G in the axiom schemes of scheme of replacement, then the generic extension will not satisfy replacement because the generic filter gives us this sequence of length omega, which is cofinal in the ordinals. Moreover, as I might verify later if time allows, this forcing does not add any new sets, which is actually not a new result. I mean, it's easy to see. And so the generic extension is just the ground model if we just consider the generic extension as a collection of evaluation of names in the ground model. And then, of course, since the ground model satisfies ZFC, the generic extension does as well. And so one question might be, can you also destroy replacement if you don't allow reference to the generic predicate that you add? And you can do this, for example, by modifying this collapse forcing slightly so that you not only add this sequence, this omega sequence, which is cofinal in the ordinals, but you also code it, for example, in the continuum function. And then this way you obtain a generic extension where replacement fails without reference to the generic predicate. But for the rest of my talk, it doesn't really matter which kind of predicates we consider for the generic extension. So what do I want to do next? So let's consider this forcing collapse omega ord. It's not too hard to see that this forcing actually satisfies the forcing theorem. There's a proof of this fact in Cy Friedman's book. I might give a proof later if time allows as well. Yes. And so if you do this forcing, you get this omega sequence, which is cofinal in the ordinals, and let's represent it by this function g, which is just this map from omega cofinal to the ordinals. And then an easy density argument shows you that the set of natural numbers such that the set of natural numbers n such that g of n is even is not in the ground model. But as I said before, this forcing does not any new sets.
Why doesn't it any new sets?
No, you don't. The point is that the domain of your conditions is always a natural number. So you would collapse all uncountable cardinals if the domains were just finite subsets of omega. But if you require that the domain is a natural number, you don't add any new sets. I mean, I'll try to give the proof later.
It stands for the conditions to involve ordinals that are so huge beyond the size of your name. Can you define the definition of this collapse?
It's called omega the ordinals.
so I'd rather try to give the proof at the end if time allows, but not spend too much time on it now. I hope I'll get to it.
The functions are increasing.
No, you don't have to require their increasing. But I mean, Joel just gave the argument really.
It extends that any condition can be extended to involve an enormous ordinal which is bigger than anything in the name, and therefore when you interpret the name by the filter below that condition, then you don't get anything before.
Yes.
So that's the fundamental problem, right?
I mean, basically, a single condition. I mean, you can find a single condition that decides any given name. I mean, in the yeah. So I just want to mention a theorem which I'm not going to talk about any further, which might be somewhat surprising. So assume that P is a class forcing extension that satisfies the forcing theorem. Assume P is a class forcing that satisfies the forcing theorem and which preserves all the axiom in the axiom scheme of separation. Then, in fact, it already follows that P preserves all the axioms of the replacement scheme. So it's not, I mean, like in this example, if you destroy replacement and your forcing satisfies the forcing theorem, then in fact you already destroy separation. And so I want to put a question here. So preservation of replacement, which is also called pretameness essentially, implies the forcing theorem to hold, and an obvious question would be, does preservation of separation already imply the forcing theorem to hold? So yeah, we don't know what the answer to that is. But now I want to come to actually the main part of my talk, which is about failures of the forcing theorem. So one easy observation that I want to put at the start is that if you have a class forcing for which the definability lemma holds, then the truth lemma holds for this forcing. So that's basically just looking at any standard textbook proof. We'll show you that this also works for class forcing. And so why should the forcing relation of a forcing ever not be definable? So how does the proof go for set forcing of the definability of the forcing relation? So we can build a formula that defines the forcing relation for a given formula phi by induction on the complexity of this formula. And the crucial point actually is the definability of the forcing relation for atomic formulas. That is equality and element relation. And so if the forcing relation is definable for atomic formulas, then basically the same proof as in set forcing shows that it's definable for all first order formulas. And for atomic formulas, we have, like in set forcing, the following equivalence. We say that the condition P forces that the name sigma is an element of tau, if and only if, well, there's a dense set of conditions forcing some, in this case, some equality below names sigma and rho is a name which is of smaller rank than tau. And then for equality, we have a similar definition, and then you get an inductive definition on the ranks. And the problem, though, is that in each step, when we reduce the ranks, we introduce unbounded quantifiers. And so, I mean, if we have names of infinite rank, I mean, this doesn't give us a formula defining the forcing relation for this atomic formula. I mean, the problem is that these quantifiers here are quantifiers over the forcing poset. So if the forcing poset is just a set, these quantifiers are bounded, so there's no problem. But for us, the forcing poset is a proper class here, so we have unbounded quantifiers, and we can't get a uniform way of defining this forcing relation. And so now I'm coming to the counterexample for the forcing theorem. And this counterexample is a forcing that was invented by Cy Friedman and never properly published. So let me give the definition. So we work over a countable transitive model M of set of C. And conditions in the forcing are triples of the form D, E, F with the following properties. So D stands for domain. the domain is a subset of omega, it's supposed to be a finite set, then we have an acyclic relation E on D, and we have a function f which goes from its domain to the ground model M, and the domain, for a kind of technical reason, is supposed to be either empty or the actual domain D. And so now the last point is the key point. So f is supposed to be an injection, and if the domain of f is not non-empty, then we want that this relation E reflects what the images of f, how the images of f behave under the epsilon relation in your model M. So I mean, E is just an isomorphic copy of the epsilon relation on the range of f. And the oh yeah, I should maybe say what the ordering is. So the ordering is again the natural ordering. So you, if conditions get stronger, the domains D grow, the relations E grow, then the relation restricted to the old domain is just the old relation, and the functions grow. And so the idea of this forcing is, I mean, by an easy density argument, this component f here will add a bijection between omega and the ground model, and then these components E, they will grow into a relation on omega, which is just an isomorphic copy of the epsilon relation of your ground model. So I think I'm saying this on the next slide. Yes. And so you get this property here. You get that your ground model satisfies some formula phi of x if and only if there is a natural number n, which f, so f is this bijection that you add, big F now, and big E is this relation on omega. So the ground model satisfies a formula phi if and only if there is a natural number n such that n gets mapped to x by your bijection, and phi relativized to this structure omega with this E relation of n holds. So you get, I mean, you're very close to getting a truth definition for the ground model. And I mean, that's the idea. So I give another equivalence here. So this is equivalent to saying that there is a natural number n, and the condition in the forcing such that the f component maps n to x, and such that the condition P forces that phi relativized to this structure omega with the relation E holds of n.
Assuming the forcing theorem.
Yes. I mean, this is only expressible over M if the forcing relation is definable. Yes. Which is kind of the point of the first part of the proof. So Friedman introduced this forcing to observe that the forcing relation for first order formulas with quantification only over omega, or let's say with bounded quantification, is not uniformly definable for f. And why is this? Because if this was uniformly definable for this forcing, then we would get the truth definition just by the above equivalence. So I mean, note that this is just, I mean, this, we get that the model M satisfies the formula phi if and only if some formula with quantification over omega holds true. So what do I want to say? Oh, yes. So the problem is that we don't know whether these generic extensions by the forcing f have universal delta zero. I mean, have a formula which is universal for delta zero formulas. And so this doesn't straight away give us that there's a single formula for which fails the definability lemma. But with a little extra work, we will get that. So the idea is that we replace delta zero formulas with quantification over omega by infinitary formulas with junctors over omega. So that's a trivial step. And then the failure of the forcing theorem for this forcing is a consequence of the following theorem, which says that assume P is a class forcing for which the forcing relation for the equality V0 equals V1 is definable. Then there's a uniform definition of the forcing relation for infinitary formulas with parameters. And the idea of this proof is that by induction on formula complexity, we construct a definable class of triples phi together with two names, mu phi and nu phi. Phi is an infinitary formula with the property that one forces phi holds if and only if those names are equal. So perhaps there should be brackets on these sides here. So this reduces checking whether phi holds to checking whether two names are forced to be equal. And so actually this can be improved. We can find fixed names nu and mu such that the forcing relation for the formula nu equals mu, so the difference is now that we fixed two names nu and mu, is not definable. So this means that the set of conditions in the forcing which force equality between nu and mu is not definable. And the key to this is the following lemma, which says that there are names mu and nu, and there's a set of pairs in our ground model M of pairs phi and conditions q phi, such that M satisfies the formula phi if and only if q phi forces that mu is equal to mu. And so this is now, I mean, this works for parameter-free formulas, and actually one can get something similar for formulas with parameters. So that's what I mean with parameterized version here. Oh, this thing stopped working. I think I pressed some button on this side. I'll just use it. So consistently, we also get non-amenability of the forcing relation. So assume, I mean, this is now an easy corollary, kind of. Assume that M is a model in which every element is light phase definable. So such models exist. For example, take the least alpha, such that L alpha is a model of ZFC. Then we have the set X, which is the set of all conditions Q phi, as above. Set of all conditions Q phi that force that mu equals nu is not an element of the ground model. Because if it was, it would be light phase definable, and this would give us a light phase definition of truth. Of parameter-free truth over the ground model, which is a contradiction. I see. This still doesn't work. Okay, now I want to get to the main result. So as I said, the truth lemma follows from the definability of the forcing relation. And so the main result is now that you can also have a failure of the truth lemma consistently. And so we'll make use of a theorem by Hempkins, Linetsky, and Reitz, which I'm actually stating in a weaker form than the actual theorem is, but that's enough for our purposes here. So if M is a countable transitive model of set of C, then there's a set of C preserving, that's just what tame means really, class forcing P, and a generic extension by this class forcing in which every ordinal is light phase definable. And in fact, the result is that every element is light phase definable, but we won't need that here. And if the ground model satisfies that V equals L, you can do this by a very simple forcing. You can just, in the first stage, add a Cohen subset U of the ordinals, and then perform a reverse Easton iteration that codes U into the continuum function. So that's sufficient under the additional assumption that V equals L. And so, I mean, but you have to be careful in the choice of Cohen subset of ord. I mean, so not every generic extension of this model M by this forcing will be pointwise defined, or we'll have all ordinals light phase definable, but there is a particular generic extension in which all ordinals are light phase definable, and that can be ensured by a very careful choice of this Cohen subset U of the ordinals. But I'm not going into the details of this. Another lemma that I'm going to use is the observation that if M is a countable transitive model of Kelly-Moore's class theory, then M does not have light phase definable ordinals, and I think there's a proof on this slide.
What does that mean? I mean, 0 is light phase.
Yeah. Sorry, to have light-phase definable ordinals is supposed to mean every ordinal is light-phase definable. You're right, of course. Of course, your version is slightly too strong. Why is that? Because in Cayley-Morse, in models of Cayley-Morse, we have a second-order truth predicate. I mean, the truth predicate is a second-order object of a model of Cayley-Morse. And if every ordinal is light-phase definable, then we get, as a second-order object, a bijection between omega and the ordinals, because we can just define the object which maps a definition to the ordinal it defines. And, well, this contradicts the axiom of replacement. And another lemma that we're going to use is that if P is a tame class forcing, tame just means preserving the axioms of ZFC. For a Cayley-Morse model M, and you have a generic filter for this forcing, which is Cayley-Morse generic, which means it doesn't only intersect all the dense subclasses of the forcing, but it intersects all the second-order objects of your Cayley-Morse model, which are dense in the forcing. Then the generic extension is again the underlying set of a model of Cayley-Morse class theory. So essentially, if you start with a model of Cayley-Morse and you perform tame class forcing over this model, you will again get a model of Cayley-Morse. I should hide this, otherwise I will try to press it repeatedly. That's what I just said. Yes. And so if we look at the forcing from the previous slide, we will get for every condition in the forcing, we will get a generic filter, so that in the generic extension, not every ordinal is light-phase definable. So why is that? Well, because take any condition in this forcing. So this forcing was this two-step iteration, which first adds a Cohen subset of the ordinals and then codes it into the continuum function. So if you take any, if you start with a model of Cayley-Morse, take any conditions, and now take a Cayley-Morse generic, then the generic extension satisfies Cayley-Morse, and thus by this lemma, it cannot have all ordinals light-phase definable. I mean, it's a triviality. And so that's the main theorem. If M is the underlying set of a countable transitive model of Cayley-Morse, to be the underlying set just means to be the first order part. Then the two-step iteration of this forcing P, so that's the forcing which potentially adds a generic extension, which potentially produces a generic extension in which every ordinal is light-phase definable. So the two-step iteration of this forcing, together with Cy-Friedman's forcing that I introduced before, does not satisfy the truth lemma over the model M. So this means there is a first-order statement which holds in some generic extension, but there's no condition in this generic filter which forces this statement. And this is a consequence, a trivial consequence of the following theorem. The theorem says that if M is a countable transitive model of ZFC, and P is a class forcing for M, so P, when we want to prove the main theorem from this theorem, P will be this two-step iteration that I just mentioned. So assume M is a countable transitive model of ZFC, and P is a class forcing for M, which preserves the axioms of ZFC, such that there is a generic filter for this forcing, such that the generic extension has light-phase definable ordinals, which means all ordinals are light-phase definable. And for every condition, we also have a generic filter, such that the generic extension does not have light-phase definable ordinals.
Is little p a member of G bar?
I'm sorry?
Is little p going to be a member of G bar? For every little p in G, there's a...
No, I mean we have a fixed generic filter G.
In condition 3, you've got for every little p in G.
Yes. So
the little p is never used again, and it should be that G bar contains it.
Oh, you're right. Sorry. Yes, that's yes. So yes. So for every p in G, so in condition 3, it should actually say for every condition p in G, we get the p generic filter G bar that contains this condition p. Of course. Yes. Thanks. and such that this generic extension does not have light-phase definable ordinals. So this means there are ordinals in this generic extension which are not light-phase definable. Then the truth lemma fails. The truth lemma fails for the two-step iteration of this forcing P together with the forcing, with Seyfriedman's forcing F. And, maybe I should say, so why does the main theorem follow? I think I have this on the next slide. Yes, so let me give the proof of this theorem first. So the main idea is that forcing with Seyfriedman's forcing makes the property of an intermediate P generic extension n, so n is supposed to be the model after just forcing with this forcing P up there, makes the property of the intermediate generic extension to have light-phase definable ordinals expressible by an infinitary formula in the final generic extension. And so this is supposed to be the formula which says something like, for every n in the natural numbers, there is a formula phi such that if n gets mapped to an ordinal by the generic bijection between omega and the ground model, then n is in fact the unique natural number satisfying the formula phi in this structure omega with the relation E that we added by Seyfriedman's forcing. And but now we can first choose a generic filter for this two-step iteration with the generic G as in the second item above. So we can choose a generic filter for this two-step iteration such that the intermediate extension has all ordinals light-phase definable. But then and then assume for a contradiction that some condition P forces that this statement holds in the final generic extension. But then by the third condition up there, we can choose a generic filter that contains this condition, however, such that the intermediate extension does not have light-phase definable ordinals, so which has an ordinal that is not light-phase definable. But then, of course, this means that this condition can actually not force this statement here. So why does this imply the main theorem? Well, I guess that should be pretty clear now. I mean, that's what I just proved, really. Yes. Okay, so I have lots of time left, so I can come back to Motigitik's question. However, I will not give the easiest proof of. So let me maybe remind you what I claimed in the beginning. So we had this forcing collapse omega ord, which was the collection of all P from n to m. So m was our ground model, and n is a natural number. And okay, so let me start with a definition. The definition is the set decision property, and we say that a class forcing P has the set decision property if whenever we take a set of conditions in the forcing and one condition P in the forcing, then we can strengthen it to a condition Q which decides every element of this set. So A was this set, and deciding it means that either this condition Q is stronger than, so for every element little a of big A, either Q is stronger than A or Q is incompatible to A. And this is just equivalent to saying that
Is one by one?
I'm sorry?
Again, the definition, do you mean P one by one bijection? No, in the definition of collapse.
In the definition,
Yes.
these one-to-one injective?
No, not necessarily, no.
But then it covers omega 1. The range.
Yes, but there's no name for this collapsing function. So I mean, you're right. Of course. So let's say let G be the union of. I shouldn't call it G. Sorry. Let F be the no, let F be the set of all pairs n comma alpha in G. So G is supposed to be the generic filter now, such that alpha is less than omega 1. So you're right. This is a surjection from an infinite subset of omega to omega 1. But the point is that this F does not have a name in the ground model. That's why omega 1 is not called F. So I mean, you cannot find a name for F, basically because let's see. I mean, I'd prefer to give the more complicated proof of this fact. But the point is that I mean, you can't find a name for this F. Oh, maybe I should give it.
Or even for the domain of F.
The name of the set.
Well, yes, you can. Yes, same thing. Okay, let me come back to the set decision property. So the set decision property means whenever you have a subset A of your forcing and a condition P, you can strengthen it to a condition that decides the intersection of the generic with your set A. And what is easy to see, if a forcing P has the set decision property, then P does not add new sets. And the idea here is that, oh, I think I have a proof on the slide. I shouldn't do it on the blackboard. Yes. So the proof of this is that assume sigma is in the ground model and is a name for your forcing. And let big A now be the set of all the conditions that appear within the name sigma, so like in its transitive closure. And let P be any condition in the forcing. So by the set decision property, we can strengthen P to some Q, such that for every element A of your set big A, either Q is stronger than A or Q is incompatible to A. So that's just the use of the set decision property. But such a Q will decide the evaluation of sigma by a generic filter. Yes, because I mean yes, I mean that's just this equivalence that I stated up there. I mean Q decides the intersection of the generic filter with the set big A, so it decides which of the conditions that appear in the name sigma are in the generic filter, and then of course it will decide the evaluation of this name. And it's easy to see that if you can decide names by conditions, you will get the forcing theorem easily. Basically, because if you have, oh, maybe I have the proof on the slide again. No. So assume you have like a statement, statement sigma equals tau, and you want to know whether P forces that sigma equals tau, and this is equivalent to saying that for every condition Q, which is stronger than P, if Q decides sigma, then we get that sigma evaluated by Q is the same as tau evaluated by Q. And I mean this means sigma evaluated by the generic, but if you know that Q is in the generic, you know what sigma evaluated by the generic will be. Okay, and so perhaps slightly more surprising is that if you have a separative class forcing that does not add new sets, which means that no generic extension by this forcing has new sets, then your forcing actually has the set decision property. And the idea of the proof is that start with a set big A and a set and the condition P in your forcing, and look at the name sigma, which is just the name for the intersection of the generic filter with your set A. And assuming that no condition, no strengthening of P decides the intersection of the generic filter with the set A, we can from the outside construct the generic filter such that the evaluation of sigma with the generic filter is not in the ground model. I wasn't planning to talk about the details of this, but so with this idea it's not too hard. And this leads to the corollary that class forcing, which doesn't add new sets, always satisfies the forcing theorem. And I think, yes, now I want to argue that this collapse forcing actually satisfies the set decision property, which is easy to see. And then, of course, this implies that it doesn't add new sets, and it also satisfies the forcing theorem. Oh, I think this is just a reminder what the set decision property is, and now I want to show that this collapse forcing satisfies the set decision property. And so the proof is we start with some subset of this collapse forcing and some condition P in the collapse forcing, and now we want to find this strengthening Q as is needed for the set decision property. And so what we do, I mean, this is basically what Joel hinted at before already. We let alpha star be the supremum of all the values of A of n, where A is a condition in this set big A, and n is in the domain of A. So, I guess what I really want here is the supremum of the rank of all the values of A of n, because A of n is just some element of the ground model. I guess I was thinking of ordinals.
You should add one, or something. You want it bigger if there's a max or something.
Do I have to add one? Yeah, probably.
It's free, so just do it.
Sure. Okay, let's add one. We don't have to think about it. Oh no, I added one here.
Change your slides very quickly.
Yeah. Okay, so what I do now is I take this condition P and I just add one component. So at the top of P, I add this alpha star plus 1. And then it's very easy to say that if you take any condition in the set big A, either Q is stronger than A or Q is incompatible to A. And that is because Q just has a component that is larger than anything that appears in A. So either, if you are in big A, you can either be an initial segment of Q or you're incompatible to it, because if you're not an initial segment, you will definitely have a value here which is smaller than alpha, or smaller, less or equal than alpha star. And yes, I mean, this is essentially just the basic argument that you could do for this collapse forcing in slightly more generality, really. Okay, and yeah, as I said, this shows that this simple collapse forcing, oh yeah, you're right, the range are the ordinals, satisfies the forcing theorem and doesn't add new sets. Okay, and so I think I have another positive result that I wanted to talk about. So this is some history first. Zarach in 1972 showed that if a forcing P is supposed to be a class forcing, is the increasing union of a sequence, of an order-length sequence of complete subforcings, then the forcing theorem holds for this forcing. In particular, this implies that the forcing theorem holds for any iteration or product of set forcings. And however, this is just a note. This is not sufficient for set of minors preservation. And so what we also did is to find a weakening of this condition, so of Zarach's condition, which still implies the forcing theorem to hold, but is more widely applicable. And for example, it can also be applied to this simple collapse forcing to give yet another proof that this collapse forcing satisfies the forcing theorem. And this property is called approachability by projections. So it's, I mean, the idea is somehow related to the union of complete subforcings property. So we say that the class forcing is approachable by projections if it can be written as a class length union of a sequence of forcings P alpha, for which we have a sequence of maps. These will be projection maps, pi alpha plus 1, and alpha is in the ordinals. So pi alpha plus 1 is a map from the whole forcing P to this forcing P alpha plus 1, and we have some properties. So the first three properties just say that pi alpha plus 1 is a projection map. So it should map the trivial condition to the trivial condition, so the trivial condition of P to the trivial condition of P alpha plus 1. If we have two conditions in the forcing P, P and Q, and P is stronger than Q, then we want that the image of P is stronger than the image of Q, so it's order preserving. And we want that for every condition, if we have a strengthening of the image of that condition, then we can strengthen the original condition such that the image of this strengthening is stronger than that strengthening. So we have like this. So we have P, and then we have this map pi alpha plus 1, and then we get pi alpha plus 1 of P, and then we take a strengthening, so this is now Q, and then we can take a strengthening R here, and then what do we get? Oh yes, so then we get pi alpha plus 1 of R, and this is stronger than Q. So this just means that these pi alpha plus 1s are a projection each, and then we have two additional conditions. The first one says that if we have actually a P which is in P alpha, not P alpha plus 1 here, and the condition Q in the big forcing P, and if the projection of Q is stronger than P, then this can only be the case because Q was already stronger than P. And the fifth condition is that the pi alpha plus 1s are actually the identity on P alpha. And as I already mentioned, we have by conditions 1 to 3, we have that the pi alpha plus 1s are projections. And we also get that if you have a generic filter for the forcing P, I mean, then the projection, the images of G and the projections are generic for those initial segments. And so this is sufficient for the forcing theorem to hold. So the theorem is that if P is approachable by projections, then the forcing theorem holds. And moreover, every new set is in a set generic extension of the ground model. Namely, it's in a generic extension by one of the P alphas. And this is, in a certain sense, a weakening of Sarach's condition. So if P is the increasing union of a sequence of set size complete subforcing, so this was Sarach's requirement, then it's in fact equivalent in a strong sense to a forcing which is approachable by projections. So in particular, this equivalence implies that the forcing extensions are the same. And so I have two examples here, namely this simple collapse forcing, which I should not have erased a couple of minutes ago, collapse omega ort, and its variant collapse star omega ort. And collapse star omega ort, I think I'll just put it on the blackboard again. So collapse omega ort was the collection of all functions P from n to the ordinals, where n was a natural number. Now collapse star omega ort is the collection of all functions P from, say, x to ort, where x subset omega is finite. And so these forcings look very similar, but actually there are huge differences. So as I already said, this collapse forcing here doesn't add new sets, but this collapse forcing collapses all uncountable cardinals. So
one is dense in the other.
And one is dense in the other. So I mean, that's an observation that one can make here, that if you have two class forcings and one is dense in the other, this doesn't really mean much for the generic extension. So they can be very, very different. So, I wanted to argue. I wanted to argue why these forcings are approachable by projections, and so the only thing you really have to do is write down what these projections are. So, and how do we do this? So we want to define these pi alpha plus 1 maps, and the idea is that pi alpha plus 1 of a condition P, so it doesn't really, so the projection maps will be the same independently of the forcing, at some, let's say k, or let's say, yeah, k is supposed to be the same as P of k if P of k is less or equal than alpha, and it's supposed to be alpha if P of k is greater than alpha. And now it's very easy to verify that all of these statements hold with these projection maps. So this quite quickly shows that both these collapse forcings satisfy the forcing theorem. Yeah, it's really elementary calculations. And I think this means I'm almost finished. Oh, one thing I wanted to say is that this is not a necessary condition for a forcing to satisfy the forcing theorem. So, for example, Jensen coding satisfies the forcing theorem because it preserves the axioms of set of C and does this pretame. But it's not approachable by projections because Jensen coding adds a real which does not exist in any set forcing extension. But I think on 2 slides ago I showed that whenever you add a set by a forcing that is approachable by projections, it will be in a set forcing extension of the ground model. So, yeah. That's it. Thanks.
Thanks very much for that. So here all the partial orders are all definable, even if sometimes the forcing relation isn't definable. But often you're working in models of MK here, so does anything interesting happen if you drop the restriction on definability of the initial partial order?
No, not really. So in fact, I mean, there's a paper related to, there's a paper, we wrote a paper on this. And so in fact, we're working in a more general context there. So we're working with second order objects where we allow the partial order to be a class there. So I mean, but I wanted to like keep the context simple for this talk. But I mean, you can basically do the same thing with second order models.
You had this example P star F where you had the non-definability of the forcing relation.
Yes.
Right. So can you also get a specific, a simple formula like like tau equals sigma, whose truth is not definable?
Yes, I mean by the theorem that if the truth, if the forcing relation is definable for atomic formulas, then it's definable for all formulas. Okay. So whenever you find some formula where it's not definable, you can trace it back to some atomic formula. Yes. Yes.
I have a question about this collapse omega orb that, or if you do say collapse omega comma v instead, I mean with just this, then isn't this dense in the Friedman forcing? Because if I have some finite sequence of sets, of course it tells me what the epsilon relation is, and then it's like this little v thing that you're doing. So it seems like I have a map from collapse omega v into f. And the thing that Friedman is adding really is the case when the domain of your little f is empty, right? Yes. Isn't that what's making it work? I mean,
I think the main point that this relation on omega gets a name.
Exactly, and it gets a name because you're sort of adding in this empty set condition where you haven't put the labels.
Oh, yes, you're right. So I said this is kind of a technical details, but you're right. It's in some sense it's also the main point, really.
So one could also just think about collapse omega v, but then in addition to those conditions, you also forget the actual sets and only remember the epsilon relation on that finite tuple. And then this is basically the same as the Friedman forcing, right?
I guess that should be true, yes.
More questions?
Could I ask, a long time ago there was a paper by Chuakwi about forcing.
By whom?
Chuakwi, Rolando.
Oh, yes.
About extending models of Morse-Kelly by forcing. I was just wondering, how are his ideas related to yours?
I'm afraid I haven't read his papers.
Oh.
So yeah. Oh, I could say, so there's also a poster related to this paper which explores things that I didn't talk about, namely the connections between the between the forcing theorem and the existence of Boolean completions, which is out on the corridor. So if you're interested.
Well, thank you again.